So this semester I was tasked to analyze the different OST responses to different heat applications. More specifically, I was going to examine the different responses due to a point-like heat source where a temperature wave propagates spherically and a heat source in a linear environment where temperature propagates somewhat linearly throughout a tube. So the purpose of the study is to localize or find quench spots in SRF cavity. So what happens is that when a thermal breakdown occurs or a multipacting in a cavity, it might heat up defects within a tube. However, if the heat is not removed fast enough by the surrounding superfluid helium, it might reach critical temperature, which is around 9.2 Kelvin, thus quenching the spot and turning the superconducting niobium to normal conducting niobium. Modern techniques use temperature mapping, however, this requires hundreds and thousands of temperature sensors and can be expensive. A powerful alternative currently in development is the use of OSTs to triangulate the position of a quench by utilizing the properties of a second sound wave. Because we know the velocity of the second sound wave, we are able to triangulate the position of the quench spot. So why are we using the second sound? So the second sound wave is an entropy modulated wave in superfluid helium. We use this because it is much slower than the first sound, and so it is easier to detect. As you can see here, the operating region of constant velocity is also quite high, between 1 and 2 Kelvin, which is below the critical temperature of helium. And for our purposes, we'll be operating around 1.5 to 1.8 Kelvin, and so the average velocity of the second sound will be about 20 meters per second. So an OST in general consists of a device with a semi-permeable membrane, which allows only superfluid helium through. And due to fluctuations of the superfluid helium and the normal fluid helium, the membrane will oscillate. So these oscillations are brought about by something such as the second sound wave. We use this to triangulate a position by arranging it in some sort of geometry around the multi-cell cavity. As you can see in this figure, which is from the response of an oscillating superleak transducer due to a point-like heat source, they were able to determine the spot by examining the different arrival times of the second sound wave. So first I was tasked to analyze the response of an OST to a point-like heat source. So Andre simply gave me the data for this, and I was not involved in the experimental setup. So I will go briefly on what the setup was. So it was arranged in open geometry where the heat source was placed 10 centimeters away from the central OST. And there are two peripheral OSTs which are about 3 centimeters greater in distance. And we applied different pulse durations and strengths as outlined here. So first I looked at the amplitude response. I didn't go too in depth in the OST's response to the pulse amplitude. However, I did look at the relative amplitudes between the OSTs. Namely, I looked at the difference between the central OST and the peripheral OSTs. So here in these diagrams, channel 1 and 3 represent the two peripheral OSTs, and channel 2 is the central OST. Between channel 2 and channel 1, we see that the magnitude is 5 times greater. And note that these signals are just different samples I chose with the same pulse power. However, if we look at the intensity relation, we see that intensity is proportional to the inverse square of the distance. And so if we take the ratio between the intensities of the outer and inner OSTs, we get a ratio of around 1.69. And so the central OST should be 1.69 times greater than the outer two. However, this is much smaller than what we got experimentally. And so we can conclude that there's something going on. In other words, that the second sound wave is not propagating as an ideal sphere, but rather it is more concentrated along the normal of the heated surface. Next, I looked at the frequency response of the OST signals. So for this, I used a time result Fourier transform because I wanted to isolate the OST signal in time. I took averages over pulses with similar pulse lengths. This is because I found that the waveforms were very similar despite the different amplitudes. So averaging we over the 10 microsecond, the 100 microsecond, and the 1 millisecond, we get a dominant frequency of about 1.53 kilohertz. However, the uncertainty associated with this measurement is quite high, as you can see, as the peaks on some of these averages are not as prominent, especially in the 10 microsecond data. So where does this frequency come from? So we concluded that this does not come from the OST circuitry. This is because the preamplifier actually attenuates all those frequencies, and so we should not see any of those. So those range from 365 hertz and lower. So the next question is this oscillation characteristic of all OSTs in general, or only our specific OST? So in comparison with the frequency Connor-Daly and the Göttingen, researchers found our frequency was different from theirs, and whereas Connor's and the other research group was also different as well. And so because of these inconsistencies, it seems like the frequency response is characteristic of only our specific vibrational eigenmodes. So the problem with the open geometry is that the intensity drops off dramatically, as we can see from the amplitude responses. Because of this, the waveforms actually become more deformed as the pulse signal gets weaker and weaker. And so around 12, 10, 8 volts, the waveforms seem consistent. However, below that, it starts to be attenuated and deform in some way. And so it would be interesting to see if we can restrict the geometry so that we can get a heat signal without a high energy drop. And so this is the basis for our second experimental setup, where we restrict the heater and the OST to a linear environment, as we can see in this figure. Here we place a heater on one end of a G10 tube and place an OST towards an open end. And ideally, the wave should propagate linearly throughout the tube with little energy loss. This is because instead of a spherical wave where the intensity starts to thin off as the distance increases, the thickness of the heated helium should ideally stay constant, assuming G10 is a perfect insulator. And to measure the energy throughout the tube, we place bolometers, as you can see here, T1 and T2 throughout the tube. So here is our general setup. On the right, we can see the cryostat where we place the setup in, and to the left, we see the associated electronics. So the OST is connected to a preamplifier, which acts as an amplifier and a high-pass filter, where the OST has a 400 gain, and the high-pass filter attenuates frequencies of 362 hertz and lower. And the bolometers, or the ruthenium oxide temperature sensors, are connected to a 200 gain. And according to the article on Cernox temperature sensors, the time constant is given to the right and was calculated to be approximately 500 nanoseconds. This is only an order of magnitude calculation, since the uncertainty is great due to the small measurements that were needed. So, next we wanted to determine some sort of relationship between the temperature inside the Dewar versus the voltage across the resistors, or across the bolometers. So given our temperature voltage relation, we took a linear regression with an R-squared value of 0.099, as shown below. We took the derivative in order to find the relationship between the change in voltage and the change in temperature. We wanted to know the change in temperature rather than just the relationship through a function, because when we measure the voltages across the bolometers, we cut out the DC part of the bolometer. And so we will only see the waveforms, which will only indicate the change in temperature. In order to determine the actual temperature of the pulse that's going through, we use the formula. The change in temperature is equal to the energy determined by Kirchhoff's law, which is v squared divided by r times the length of the pulse divided by the specific heat of the helium, the density of the helium, and the volume of the chunk being heated. And the volume is determined by multiplying the circular cross-sectional area of the cylinder, which is pi r squared, times the height, which is the velocity of the second sound, times the pulse length. To illustrate this calculation, we calculate the expected value of, let's say, a 32 watt per centimeter squared signal with a duration of 10 microseconds. Using those formulas above, we find that the delta T should be around 5.56 millikelvins. Looking at the experimental values, for a 32 watt per centimeter squared pulse at 10 microseconds, we find that the closest temperature sensor has a change in 5 millikelvins, and the second temperature sensor has a change in 4.5 millikelvins. And so using this, we have an average of 0.5 millikelvin change between the two temperature sensors, and so the energy seems to be quite constant throughout the tube. So now we're going to look at the frequency response, where we conduct the same time result fast Fourier transform. However, here we see that across the different pulse lengths of 1 millisecond, 100 microseconds, and 10 microseconds, we see that the curves closely resemble one another, and we can see that the dominant frequency is distinctively around 910 Hertz. Now, the question is, where does this frequency come from? So again, we can conclude that it's not because of the OST circuits, since it is those frequencies are attenuated by the preamplifier. However, if we look at the Göttingen frequencies again, 910 Hz is most similar to the result of 890 Hz with a 5% error. And so this gives us the question of, is it the second sound frequency, or is this actually a typical OST response due to the second sound wave? Well, it is not the second sound frequency due to previous experiments done with diffraction. Given the frequency of 910 Hz, the researchers previously doing diffraction would have found diffraction behaviors. However, this was not a case and there were no such signs. Therefore, it couldn't be the second sound frequency. Is this response typical of all OSTs? Maybe. Because we do not have a large enough sample size or not enough experiments to confirm, we cannot exactly say whether or not this is typical of all OSTs or just typical to ours, which is very similar to Göttingen's results. So from this experiment, we see that the energy drop throughout the tube is small compared to the open geometry. And so I feel that this would be useful in future experiments where you would want to pinpoint the characteristics of an OST or the second sound wave. So unfortunately, I was unable to analyze the data fully since I've only had a week since the experiment. So interesting things to do with this data would be to try to map the amplitude response and the temperature input due to the wave and see if there is a relationship, although it seems that it is highly nonlinear. Also, it would be interesting to see other experiments to be conducted with this restricted geometry as stated before. Thank you.